to finish chapter 6, we're going to pick up kind of with the topic we left off, mole ratios. So we had talked about how to write ratios between reactants and products of a chemical reaction. And as this slide says, it is the same idea with ionic compounds dissociating into ions. So here we have the compound magnesium hydroxide, which will dissolve or break into its ions of magnesium and hydroxide. 1 magnesium, 2 hydroxide. So what these blanks indicate is that for every 1 mole of magnesium hydroxide, we will get 1 mole of magnesium ions and 2 moles of hydroxide ions are produced. Okay, so again, we're just looking at the coefficients. Understood 1 with magnesium hydroxide and magnesium, and then a 2 in front of hydroxide, showing us the ratios between the ions that we'd get from the compound. This slide is a little bit of a review, but it's very helpful to get you going on mole ratio problems and conversions between mass as well. So this reminds us, if we have moles of one thing, moles of substance A, and your problem asks you to convert like how many moles of B would you get or would you need? This is a one-step problem, all you do is use the mole ratio between those two substances. You can also convert back vice versa between moles of B and moles of A. If you have the moles of something and you're asked to calculate the mass of that thing, notice our substance is A both times. So we're not converting to a new substance, we're just calculating between the moles and the mass of a substance. Remember, we will use molar mass and vice versa. If you have the mass of substance A and you're asked how many moles, you will use the molar mass. If, however, you're given the mass of substance A, for example, like 10 grams, and the question asks for how many grams of substance B you might need. For example, if your chemical reaction was this A plus B make AB2. If we have 10 grams of A, how many grams of B do we need? We will have to use both what? Both mole ratios and molar mass. This actually ends up being quite a longer 3-step problem. The first step is that you plug in, if you're going from the mass of substance A to the moles of substance A, that's actually the first step. You're going to use the molar mass. Right? Then we're going to convert from the moles of substance A to the moles of substance B. For this, we know, according to our other diagram, we'll need a mole ratio. And then how do we go from moles of substance B to mass of substance B? We will use step 3, the molar mass, but this time for substance B. This one appears for substance A. So it's a 3-step problem to convert from the mass of one thing to the mass of something else. So let's do a practice. I don't actually have, don't worry about scanning the QR code. We're just going to work this out together. 3AB2 plus 1 mole of C2 will get us 2 of CB3 and 3A. So the question is, how many moles of CB3 would be produced from 5 moles of AB2? So again, we're given moles of substance. We could call this substance A, and we're asked to calculate how many moles of substance B. So according to our chart, we want to use the mole ratio between these two. So we're going to start with 5 moles of AB2. And I'm going to set up a T-chart, and right here is where we want to plug in a mole ratio. We want to cancel moles of AB2, and we want to convert to moles of CB3. At this point, all you do is you plug in the coefficients in the balance reaction. So 3 moles of AB2, 2 moles of CB3. And then we're going to see how moles of AB2 cancel. Don't cancel out the numbers, just the units there. And we'll do the math. 5 times 2 is 10. Divided by 3 is going to give us a decimal, just 3.3. Okay, so that would be our answer. And that's an example of how you use a mole ratio to convert from moles of one thing to moles of something else. All right, now we're going to use a real chemical reaction. It says this is how rust is made. Iron, when it is exposed to the air, oxygen, reacts to form Fe2O3. So our first question says how many moles of rust, so this is rust over here. This is just iron and oxygen, are made from 7 moles of iron. So we're given moles of iron and we're asked for moles of rust. This is like the moles of A to moles of B. So we just need a mole ratio. So 7 mole, we're going to start with 7 moles of iron. The reaction's already balanced for us. So for every 4 moles of iron, we will get 2 moles of rust. So you do 7 moles of iron cancel. 7 times 2 is 14 divided by 4. 3.5 moles of Fe2O3. Okay. Next, the question says, how many moles of rust are made from 83 grams of oxygen? All right, so we can think of oxygen as our substance A, and we can think of rust as our substance B. So let's go up and figure out the path that we need to take here. So on these diagrams, this says what you can do if you're starting off with the moles of something. But we're not starting off with the moles of anything. We're starting off with grams of, what was it, oxygen? Yep, grams of oxygen. So we're starting off with the mass of, again, oxygen is like our substance A. We're not asked to go all the way to the mass of substance B, but you're still going to follow the first 2 steps of this chart. So it's not a full 3-step problem, but we're going to still need to convert first to moles of oxygen using the molar ratio of oxygen, and then from moles of oxygen to moles of rust. So we won't do the 3rd step. We don't need to convert to grams since the question just asked for moles of rust, but we are still following this diagram. So we're going to start off with 83 grams of O2. Step number 1, if we go back up to our chart, was what again? Plug in the molar mass of A to convert to moles of oxygen. So what would the molar mass of oxygen be here? If you look at the periodic table, oxygen weighs 16, but there's 2 oxygens. So 16 times 2 would be a total of 32 grams for every 1 mole of O2. So because oxygen, again, is a diatomic, we got to factor in 2 oxygen atoms, the mass of 2 oxygen atoms. So now grams of O2 cancel. And we've converted to moles of O2. Now how do we go from moles of O2 to moles of rust? That is a mole ratio. So for every, according to the coefficient, 3 moles of O2, we'll get 2 moles of Fe2. Whoops. O3. All right, that should be it. So this was step 1, mole ratio. step 1 molar mass of oxygen, step 2 mole ratio. Moles of oxygen cancel down here, and we're left with moles of rest, which is what the question is asking for. So it'll be 83 divided by 32 times 2 divided by 3, or however you like to type it in your calculator. I know people type it in different ways. Okay, that's what I got if I did that right. All right. One more. Here we go. Same equation. So it says how many grams of rest are made from 146 grams of iron. So this is going to be a full 3-part problem, because if you'll notice, I'm going to say this is the mass of substance A. It's the one we're starting with because it's the one we're given the mass of. It's asking for grams, which is a mass, but it's a different substance, so I'll call it substance B. This is a full 3-part problem. We're going to go from the mass of A to the mass of B. So think about the chart. Scroll back up to it if you need to, but step number 1, I'm going to start with 146 grams of iron. You're going to need a periodic table. I have one right here. Well, I thought I did. There it is. Okay, iron weighs 55.84 grams for every 1 mole. So I just pulled that right off the periodic table. So this is step 1. Plug in the molar mass of substance A, which for us is iron. And I like to write my substance 2 by my units, because step 2 is going to be plug in the mole ratio between iron and rest. And I know that I have moles of iron on top if I put iron right there. Okay, but if I don't write what substance I'm talking about and I just have the word 1 mole right here, then I might not write in my mole ratio. It's a common mistake I see students make, is they might flip their mole ratio and put the wrong thing on top and on bottom. But again, if you label what substance you're talking about, that will help you write your mole ratio in the correct way. So I know I need to cancel moles of iron. I'm going to put that part on bottom, and I'm converting to moles of rest. So for every 4 moles of iron, it's 2 moles of rest. And then lastly, we need grams of rest, so we need a mole ratio, step 3, for rest. So step 1 is you're always dividing by the mole ratio of substance A, plug in the mole ratio, and then we're going to multiply by the molar mass of iron. Because for every 1 mole, we need to calculate how many grams of Fe2O3 are in 1 mole. So to calculate the molar mass of iron, we know that we're going to have 2 times 55.84 units of grams, and oxygen is 3 times 16. We add all this up. Should be 159.68 grams for every 1 mole. So we've got the 1 mole part, and then I'll plug in the 159. I didn't leave much space. 0.68 grams of iron. So again, double check all your units cancel the right way. Grams of iron cancel. Moles of iron cancel. Moles of rest cancel. And we're going to be left with grams of rest, which is what our question is asking. So we'll do 146 divided by 55.84 times 2. Oops. Divided by 4 times 159.68. And I got, if I did all this right, hopefully you get the same number as me, 208.75 grams of rest. Okay, All right, this last problem, I'm not gonna do the full thing. It's quite a long problem, but I'll do half of it because the second half will essentially be the same as the first half, just with different substances in the problem. So it says you need to make 100 grams of calcium oxalate. And then, I don't know, here in the picture you see we have a picture of what an oxalate ion is. So this is a polyatomic ion, just not one we've had to memorize. There's 2 carbons, so it's C2. There's 4 oxygens, O4, and it carries a -2 charge. So this is oxalate. Then it says, so we need to make 100 grams of calcium oxalate. So calcium oxalate would be putting calcium, which is a +2 cation, with oxalate, which is a -2 anion. Right, so we just need 1 each, so just be CaC2O4. There's calcium oxalate. It says calcium chloride mixed with sodium oxalate, all right, reacts to make, so this is our first product and this is our second product, calcium oxalate and sodium chloride. How many grams of sodium oxalate? These are our reactants. Okay, I'll highlight our reactants in blue. There's one reactant, there's our second reactant. So there's a lot going on here in this problem. And then our products, I'll highlight it in a different color. This is our first product that will make calcium oxalate. We're trying to make 100 grams of it. And as a byproduct, we'll get sodium chloride. So how many grams of sodium oxalate and how many grams of calcium chloride do you need? So we're actually going to work backwards here. We're told that we are going to make 100 grams, kind of what we want the yield to be. 100 grams of calcium oxalate, one of our products. And then it kind of asks us to backtrack, well, how many grams of each reactant would we need? So we're going to do this problem in 2 parts. Part 1 is we'll take 100 grams of calcium and we will convert to grams of sodium oxalate. Sodium is Na, but it is a +1 cation. So we're going to have 2 of these to balance our -2 anion. All right, so notice this is a grams to grams problem. This is going to be a full 3-step or 3-part problem. However, we need a balanced chemical reaction before we can do anything. So let's write out in blue our reactants. So we know calcium chloride and sodium oxalate. These are our 2 reactants. These react to give us our 2 products, which is calcium oxalate and sodium chloride. And then the last thing we need to do is balance this. Oops, I did not write sodium oxalate the right way. There's got to be 2 sodiums for every 1 oxalate. So what we notice is that we have 2 sodiums over here, so we're going to need 2 on the product side, which also gives us 2 chlorines, which is great because we already have 2 chlorines on the reactant side. So I think that's the only balancing we need. The rest of the coefficients are just 1. All right, we're going to start with 100 grams of CaC2O4. And step 1 of a 3-part problem. So you think of this 100 grams calcium oxalate, this is your mass of substance A on your chart, and then you're trying to get to the mass of substance B, and that's sodium oxalate. So step 1, if we go all the way back to our chart, I'm going to scroll up, is you always plug in or start with the molar mass of substance A. So the mass of substance A for us is calcium oxalate. And then we'll plug in the mole ratio between calcium oxalate and sodium oxalate. Step 3 is we'll plug in the molar mass of sodium oxalate. So we're going to follow these through 1, 2, 3, boom, 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 to convert. The only problem is we don't have the molar mass of calcium oxalate. We need to calculate that. So I'm going to look at a periodic table, CaC2O4. We want the molar mass of this. So calcium, we just have 1, so it'd be 1 times, nope, 40.08. Carbon, we have 2 of these. Mass of carbon, 12.011. Oxygen, we got 4 of these. Add all this up. And I got 128.102 grams of calcium oxalate per 1 mole. So I'm going to plug in, remember the first step is divide by the molar mass. Whoops, 102 per 1 mole. And I'm going to write what substance I'm talking about. Calcium C2O4 oxalate. Step 2 is you plug in the molar mass between calcium oxalate and sodium oxalate. So here is, in the black boxes, you're looking at the coefficients between this one and this one. If you notice, it's a 1 both times. Okay, so the mole ratio is just 1 to 1. For every 1 mole of CaC2O4, we'll need 1 mole of Na2C2O4. And do not skip this, because numerically I know multiplying and dividing by 1 won't change your answer, but what does matter is that your units are converting. We've canceled grams of calcium oxalate. Now we just canceled moles of calcium oxalate. And your mole ratio won't always be 1 to 1. Here it just so happens to be. And then we want to, step 3, plug in the molar mass of sodium oxalate, which says for every 1 mole we're multiplying by it this time. We need how many grams? So we need to calculate that. Na2C2O4. This is quite a long problem, huh? Sodium weighs 22.98, and we have 2 of them, so 2 times that is for sodium. Carbon, we know, is 2 times the 12.011, and oxygen is the 4 times 16. So I got 133.982. That's how many grams of sodium oxalate for every 1 mole of sodium oxalate. That's what I'm going to write right up here. 133 point, what was that? 982. And this is grams of sodium oxalate. So moles of sodium oxalate will cancel. We'll be left with grams. So now we do all this problem. What problem are we talking about? We're going to do 100 divided by 128 times 1 divided by 1 times 133.982. And we should get 104.59. That's how many grams of sodium oxalate we would need to make 100 grams of calcium oxalate. And that's only half the problem, okay? The other part of the problem that we did not yet answer is right here. How many grams of calcium chloride would we also need, which would be part 2. So I encourage you, you're going to start this problem the same way we started our other problem. You would start it with, so part 2 would be down here. This was part 1. With 100 grams of calcium oxalate, and this time you're trying to convert to grams of calcium chloride. So see if you can do that one based on what we did here. And that concludes chapter 6.